Looking at the practice from problems from 9.1e, they continue to use some, real life applications. So 17 is talking about brass being a copper containing alloy, and the amount of copper in there can vary. So there's a 3-step process you can go through to find out just exactly how much copper is in there. And part A says deduce the change in the oxidation numbers of copper and nitrogen in step 1. So looking at A1, I've got copper solid becoming copper ion 2 plus on the other side. So the change is from 0 to plus 2, or an increase of 2, however you want to express that. Whereas with nitrogen, I have HNO3, which means the nitrogen's a plus 5. On the other side, it's part of NO2, which means it's a plus 4. So going from 5 to 4, this would be a decrease of 1. Part 2 says identify the oxidizing agent. Well, the oxidizing agent is the one that's reduced, so HNO3 is my oxidizing agent. B goes on and gives you some data about a student carrying out this experiment 3 times. And under B1, it says calculate the average amount in moles of S2O3 added in step 3. And so what they intend for you to use is the average volume already calculated for you. So in B1, if I've used 28.50 milliliters of 0.1 molar, I can take 0.02850 liters times the 0.1 molar, and I will find out or realize that I've got 2.850 times 10 to the minus third moles of my S2O3 2 minus. And then it says calculate the amount in moles of copper present in brass. So now you need to look at your molar ratios. So I'm going to slide this up a little bit to take a look at it. So I'll keep it here so we can see the equations. So in B2, what I did is I started with my my molar amount. Get this out of the way. So I started with the 0.002850 moles. This is my S2O3 2 minus. And what I looked at is in that third equation, I can see that I get 1 mole of I2 combining with 2 moles of S2O3. And that would then change this to I2. And then I can furthermore see that I2 combines in, I believe it's the second equation. I2 is in a 2-to-1 ratio with the copper ion. And finally, the copper atom is in a 1-to-1 ratio with the copper ion. So if I take 1/2 times 2 times 1, that would cancel out the units to help me arrive at how much copper is actually present in the brass. And as you probably can see, that means I end up with 0.002850 moles of copper atom as well, or copper solid. So then calculate the percentage by mass of copper in the brass. You have to remember that I started with 0.456 grams of the brass. And if I have 0.02850 moles of it, then in step 3 I can multiply that by, go ahead and take the 0.002850 moles of copper times the 63.55 grams per mole that copper weighs. And that, out of that 0.456, I've got 0.1811 grams of copper. I had a total of 0.456 grams. And so as a percentage, that means I had 39.7% copper in that alloy. And it says the manufacturers claim that the sample of brass contains 44.2% copper by mass. Determine the percent air in the result. So 44.2 minus the 39.7. Again, let me scroll this up, make it a little easier. Number 4 over here, I've got 44.2 minus the 39.7, and I'll divide that by the expected result of 44.2, and we're looking at right about 10% air. Question number 18 talks about H2S, hydrogen sulfide, being a poisonous gas, and again, they give you a series of equations that it can be involved with. And for part A, it says for equation 1, state which species have been oxidized and which have been reduced. Justify your answer using oxidation states. So if I look at part A, I've got 2H2S plus O2 yielding 2S plus 2H2O. So the sulfur is going to start out at a -2, oxygen at a 0. Hydrogen is going to remain a +1, so I'm not going to worry about it. Sulfur is going to become a 0, oxygen a -2. So sulfur going from -2 to 0 means it's lost electrons and it's oxidized. Well, oxygen has gone from 0 to -2, so it's gained electrons and been reduced. Part B for equation 3, state and explain what is the reducing agent. Well, when I look at part B, I've got 2H2S plus SO2 becomes 3S plus 2H2O. And this is an unusual equation because when you look at this, the oxygen is going to be -2 here and -2 here. The hydrogen is going to be +1 and +1. So it's the sulfur that's going to become both oxidized and reduced as it goes back to its elemental state. This sulfur is at a -2. So I can have sulfur at a -2 to 0. Whereas over here, I've got sulfur at a +4 to 0. So H2S is being oxidized, which makes it the reducing agent. So you can't just say sulfur, because in this case, sulfur is being both oxidized and reduced. It's being oxidized in the form of H2S, but being reduced in the form of SO2. Letter C says, predict and explain the change in pH you would expect to observe during reaction 3. Well, if I look at reaction 3, I've got H2S, which is an acid, and it's becoming H2O, which is neutral. So my H plus is decreasing and moving to H2O. So that means my pH will be increasing as it moves closer to the neutral value of 7. And finally, letter D says, removing hydrogen sulfide may help to reduce the problems associated with toxicity, but the process used here may lead to a different environmental problem. Outline why this may be the case. And for part D, you need to take a look at equation number 2, where you see that SO2 is produced. SO2 can combine with water, and when that happens, you get H2SO3, and that's a component of acid rain. So you have to be careful that in trying to help one problem, you don't actually create another problem. Number 19 says the photograph below shows blocks of zinc metal bolted onto iron posts. So this is the zinc here, and then this is the iron post that they're trying to prevent from corroding. And it says write a half equation for the reaction in which zinc is oxidized. So I've got zinc metal, ZnS, And if it becomes oxidized, it's going to lose electrons. I'm going to assume 2 since I don't know otherwise. With 2 electrons being peeled off, this would then be aqueous, and that would be my half reaction. B says, suggest why this is described as sacrificial protection of the iron. Well, what they mean is that you're sacrificing or giving up one metal to save the other. And that's because zinc will react before the iron, since it's the more reactive metal. So zinc is sacrificed to save the iron. And C says, predict what might be observed on the posts over time if the zinc blocks are removed. Well, if the zinc blocks are removed, the iron will oxidize. So what we'll see is, we'll see rust. You might see flaking. See holes eventually in the poles. That's the type of thing you can expect to see if the zinc isn't there to corrode ahead of the iron. And number 20, a student writes the following as a balanced equation for a reaction. Comment on this, including what is not correct with the equation given. Well, when you look at the equation that they've written, although the number of each kind of atom matches up, I've got 1 manganese on each side, I've got 4 oxygen, and I've got 1 tin. The problem is when I look at this is that my charges don't balance. I've got a 0 charge on this side, but I've got a -1 and a +2 for a +1 charge on this side. So that's a problem. So to write the correct fully balanced equation, I'm going to have to look at MnO4 minus becoming MnO2. Realize that I need 2H2O to help balance that, which means I need 4H plus on this side. And if I need 4H plus, then I also need 3 electrons to balance out the charge to the 0 of the right side. With the Sn, I have Sn2 plus becoming SnO2. So again, I will need water, 2H2O, and then I'll need 4H plus, and now I'll need 2 electrons on this side to balance. Looking at this, I have 3 electrons versus 2 electrons, so I'm going to need to do some multiplying here. I'm going to need to take this equation times 2 and this equation times 3 for my least common multiple of 6. And when I do that and rewrite the equation, I was left with 3 Sn2 plus 2H2O overall on the left side after it cancels between the two sides, 2 MnO4 minus 3 SnO2, 4H plus, and 2 MnO2.